Hello and welcome to lecture 17. We are still in chapter 3 and in paragraph 311.3 on boundary value problems. Now we want to apply them in cylindrical and later in spherical coordinates. Okay, let me consider, for example, the Laplacian in cylindrical coordinates. I'll rewrite it again. In cylindrical coordinates, we have the expression of the Laplacian is 1 over r partial with respect to r of r del v by del r plus 1 over r squared del square v by del phi squared, which is the second variable, plus the third variable, which is del square v plus del z squared. That's the expression. This is equal to 0. That will be equal to 0 in the case of, as we have said, in the case of Poisson's equation. Laplace's equation. For Poisson's equation, that will be minus rho v over epsilon 0. Okay? As I said last time, we have to solve this for one variable only, and we will consider symmetry with respect to the other two. Okay, let's look at a situation where we have symmetry with respect to this and that, and we have variations with respect to r. That will be, if you want, for example, if you have two concentric cylinders like this one, okay? So those are two concentric cylinders of inner radius A, outer radius B. Assume that you have the inner radius at a potential 0, let's say, the outer one at a potential V0, and you have vacuum in between, right? And you want to solve to find the potential and then the field everywhere. Now, in order to do that, you can see very easily, those are very long ones, so if you go up and down, nothing changes, so we have symmetry with respect to z. If you go round in between the two conductors and you verify, nothing varies, therefore you have symmetry with respect to these two, and the only differential equation will be 1 over r. It will be now a total derivative, not a partial one, because it's a function of one variable, d by dr of r dv by dr is equal to 0. You can multiply by r on both sides because r is different from 0. We are working between a and v. Then d by dr of r dv by dr is 0. Since the derivative with respect to r of this quantity, whole quantity, is 0, then the quantity itself, r dv by dr, is a certain constant, let it be c1. This means that dv by dr is c1 over r, and therefore if you do integrate again with respect to r, you will have v equal c1 ln r plus a certain c2. Or if you want v equal c1 over times C1 ln r over C2 or whatever. So the important thing is that you have two constants of integration. Now in that case, you know that v is equal to 0 when r is b. So this is 0 equals C1 ln b plus C2. That's one equation. Another one, when r equals to, that's at A. At A we have the potential 0, okay? And at B you have it V0, so that will be a V0 equal C1 ln B plus C2. So you have here a system of two equations, two unknowns. You can subtract them, and for example, you will have C1 ln B minus C1 ln A. C2 minus C2 will be 0 equals to V0. This means that C1 ln B over A is equal to what? V0, and this means that C1 is V0 over ln B over A. And if you want to find C2, you can find it from here. C2 from the first equation minus C1 ln A. So this means that C2 is minus C1, you have C1, V0 over ln B over A times ln A. Okay? You can check that, for example, if R is equal to A, then you can put these two in the main equation. V will be C1, which is V0 over ln B over A, minus or plus ln R, sorry, plus C2, which is this one, V0 over ln B over A times ln A. Okay? Now, if for example R is equal to, we have a minus sign here, so that's minus C2. Look here, very interesting. You can check your answer by putting the values. If R equal to A, that's ln A. So V0 ln A, V0 ln A, same denominator, it will be 0 as it should be. If R is equal to B, then you will have V0 over ln B over A. That will be ln A minus ln B, which is ln, once again, B over A. Then you can simplify these two and you obtain a V0. So that is the expression of V at any time, at any point between A and B. And from that you can find the field E equal minus grad V. Minus grad V, it is minus V0 over ln B over A, and this is 1 over ln R, its derivative is 1 over R, so this is R here. Okay? That when the derivative of this is 0 because it's a constant, this is in the direction of AR. You don't have anything in the direction of A phi and A theta. This is expected because we know that the field of cylindrical symmetry is inversely proportional to 1 over R, like the field of an infinite wire, for example. Remember, rho L over 2 pi epsilon 0 R. Okay? Knowing E, you can find also, as we did in the previous example of the Cartesian symmetry, you can find rho S here and rho S there. And by finding rho S, you will put E equal, that will be, you put E equal rho S over epsilon 0. Then you can find the rho S here and rho S there. They are not the same because those are surface charge densities, not linear ones. The linear charge density here and there are equal and opposite, equal in magnitude and opposite in size, but the surface charge densities are not the same. Let me make a pause here. What is the difference between rho S and rho L? If you take a unit length, like this one, okay, L equal 1, and you go around the whole inner surface, the outer surface of the inner conductor, then the charge on the whole lateral area for a given length is what? This is rho L. Okay? While rho S is what? Rho S, this is a unit length, then you don't go the whole round. You take a, for example, a unit length on the circumference as well. The amount of charge here is what? This is a charge per unit length and per unit width. So this is rho S. Okay? And what is the relation between the two? You can see that rho L here, the charge per unit length, is the charge on this strip, right? Per unit width times the circumference. So this is rho S times 2 pi the radius, which is A. Okay? And check the units. Here charge per unit length, so it's coulomb per meter. Okay, that's the unit. Here, coulomb per meter square times A, which is in meter, coulomb per meter. So it's very important to know how to relate charge densities or any densities, linear to surface to volume. Okay? That is if you consider symmetry with respect to phi and z and work with respect to r. Another case, and we will see in which, according to which geometry, we want now to consider what? Symmetry with respect to r and with respect to what? To v, and let things vary with respect to phi. Okay? How do we do that? Have a final look at this lovely case so that we can go to the second case. Now, the second case, try to think of a geometrical situation where you have, let me draw the system of coordinates x, y, and z. Now, how would the two conductors be in order to solve Poisson's equation or Laplace's equation with symmetry in r and z and variations with respect to phi? Look at that. If you take a conductor like this here and another conductor like that, imagine that you have two doors like this, okay? And that is the angle between the two phi, okay? You can hold this conductor. Now that conductor extends to infinity in the z-axis and in the r, in the z direction and in the r direction. Since it extends to infinity in the z and in the r direction, therefore we have symmetry in these two directions, and things only will depend on phi. This, say, is grounded, so the potential, that should be the other way around. If you join this to ground, then the potential here, V, equals to 0. Let this be connected to another potential, or it has a potential V equals to V0. Fine? So here you have, if you move up and down between these two conductors, nothing changes, so you have symmetry in Z. If you go in and out, nothing changes, because you can look at this region as many successive conductors, each of which has its potential depending on what? Depending on phi, okay? So things only vary with phi here. And you have symmetry with respect to r and z, then you have 1 over r squared, d squared now then, v by d phi squared is equal to 0. Definitely you can solve these with the presence of charge in between, and it will be Poisson's equation in that case. If you avoid r equals to 0 to multiply by r squared both sides, because if you allow r equals to 0, you have a problem, because the two conductors will be joining each other at r equals to 0, and then there will be only one conductor. You cannot have two different potentials. So you can imagine that you have a very fine long strip along the z-axis, which is an insulating material that separates conductor 1 from conductor 2. First thing, multiply by r both sides, so the total derivative d square v by d phi square is 0, then dv by d phi is a constant c1, and then v is equal c1 phi plus c2. Now imagine that this angle phi actually is the variable. Assume that the fixed angle between the conductors is alpha. Then according to this, v equals to what? Equals to 0, where at phi equals to 0. Here, phi equals to 0, you are in the z plane. So put that, you will have a 0 equals to 0 plus C2, so C2 is 0. C1 now, V equals to V0, that's V0, equals to C1 times phi is alpha, therefore V is equal to C1, which is V0 over alpha, times the angle phi, whatever phi is. And you can check that at phi equals to 0, the potential is 0, and at phi equal alpha, the potential is V0. You have V here, okay, and you have V, you can find the field, right? E equal minus grad V. Remember, when you want to find the electric field from the electric potential using this formula, you have to remember always which system of coordinates you're using. Here we are using what? The cylindrical ones. In cylindrical coordinates, the gradient is cylindrical and gradient, it is equal to AR, that's minus sign outside, AR del V by del R plus A phi times 1 over R del V by del phi plus AZ del V by del Z. This is the gradient in cylindrical coordinates. V here, as you can see, is a function of phi, the second variable, not the first one. So the electric field here is equal to what? Equals to minus A phi over R. Del V by del phi is V0 over alpha. Okay? As you can see, the electric field is a function of R. It's not a function of phi like V. What does that mean, the electric field is a function of R? Can you imagine what is the shape of the electric field lines? This is 0 and that is a higher potential. So this would expect to have positive charges here, okay, and negative charges there. And then the lines of field are like this. They start from the second conductor and they go around. In which direction? In the negative A phi, because positive A phi is in this direction. So you are running in the direction of negative A phi, number one, and the field is inversely proportional to R. Can you see that? What does that mean? It means that very close to the z-axis, when R is very small, the lines of field are very close to each other and the field is intense. As you increase R, come here, then the two conductors will be, imagine the situation like this one. Those are the two conductors, okay? Near the vertex here, the field is very intense. Very far away from the vertex, you will have a smaller and a smaller field. More than that, very close to the z-axis, the intensity, the surface charge density is larger. Because this, as you know, at the surface of the conductor, E is rho s over epsilon, okay? So not only the field varies, even the density, surface density of charge varies. As you go very far away from the z-axis, the electric field decreases and the surface charge density, it remains positive here and decreases, remains negative there and decreases. Okay? So this is a very important, I'm trying to stress on the physical concepts behind the mathematical calculations. Our job and your job is not to make extremely difficult mathematics. You can do that in mathematics courses. Our task is to make simple math and try to understand the physics behind it. Okay? Right, so this is as far as what? As the cylindrical coordinates are concerned. Now, remember that in cylindrical coordinates, we have used only two variables. Now, if you fix this and that, then this will be similar to what we did in the Cartesian coordinates because it's the same z-axis. Okay, so you're back in the example we did for the y variation. If you remember last time, it will be you replace only z by y. Now for spherical, this is the following 3, 11, 4 now, the spherical coordinates, or solving boundary value problems in spherical coordinates. In spherical coordinates, you will have a different, to start with, a different Laplacian. The expression of the Laplacian in spherical coordinates is, let me write it down here. It is Laplacian of V is equal to 1 over r squared del by del r times r squared del V by del r plus, that's the first term, 1 over r squared times sine theta. Inside you have a sine theta del V by del theta plus the third term, which is 1 over r squared sine squared theta del square V by this one is we have a del by del theta outside. Why? Because it has to be a second order. This is second order derivative. That was first. So there has to be a partial derivative outside by del phi squared. Okay? Here, as we did in the case of cylindrical coordinates, we are not going to solve boundary value problems with 2 and 3 variables. We will consider symmetry in 2 variables and solve it in terms of the third one. The easiest situation to start with is which one? Is a geometrical situation where we have a spherical symmetry number 1, and we have symmetry with respect to phi and theta, and let variations take place with respect to r only. This will happen in which case? If you have, say, 2 concentric spheres, with this being grounded at potential V equals to 0, the inner one of radius A, the outer one of radius B at a potential V0, for example. Okay? Now, in this case, as you can see, if you vary phi, right, nothing varies. If you vary theta, nothing changes. The only variation is in terms of r. And in that case, you will have a 1 over r squared d by dr, total derivative now because function of one variable, r squared again, dv by dr is equal to 0. Again, we are not close to 0, so we can multiply by r squared, which is different from 0. We want to work between a and b. So this means that the partial derivative with respect, the total derivative here with respect to r of r squared dv by dr is 0. Remember, we are always trying to solve now Laplace's equation. We can do the same thing for Poisson's equation, but you have to put here minus rho v over epsilon 0, and your rho v could be constant or depends on r, as we have seen in the example of Cartesian coordinates. The d by dr of a function is 0. It means the function itself, r squared dv by dr, is a constant. So this means dv by dr, r big here of the spherical coordinates, is c1 over r squared. This means another integral, it will be a minus c1 over r. Its derivative is c1 over r squared plus another constant c2. Okay? Now you can, in terms of the radii and the values of the potentials at both sides, you can find c1 and c2. In this particular case, v equals to v0 and r equal a, so 0 equal minus c1 over a plus c2, and v0 is minus c1 over b now plus c2. if you subtract these two, what do you obtain? You obtain a V0 equal minus C1 over B plus C1 over A. Okay, so this will give you a V0 equal C1 into 1 over A minus 1 over B. That is a relation. So C1 is V0 over this. It will be an AB here and B minus A down there. That will be C1. Now C2, you can find it from here. C2 is equal to C1 over A, so it's V0 AB over A into B minus A. You can check. Now you put C1 and C2 here in their places, number one. Number two, you can check that at A equals to 0, at R equals to A, V is 0, and at R equals to B, V equal V0. Number two. Number three, you can find what? E from V minus grad V, but you have to use this again in which system? In the spherical coordinate system. And you take it, grad, that will be a minus IR del V by del R only, because you don't have V doesn't depend on theta and phi. So the second term and the third term of the gradient will be 0. You can find E. After finding E, once again, you can find the surface charge density on the inner and the outer conductors. Do you expect them to be the same? Definitely not. You will expect to find a higher charge density at the lower one and a smaller charge density at the upper one. You expect them also to be of opposite signs, and you would expect that the total positive charge here equal to the total negative charge there. So when same charge is distributed over different spherical surfaces, then it will have a smaller charge density on the larger surface and larger charge density on the smaller surface. Okay? So this is if it is a function of R. Now, what else do we have? We still have two cases when we have symmetry with respect to what? Symmetry with respect to R and theta, and variation with respect to phi, as in this case. In that case, this is very similar to the case of phi in spherical coordinates, because that will be 0. Away from R equals to 0 and sine theta equals to 0, you will have d square V by d phi square equals to 0. Same solution as in that. In the case of the phi, variation of phi in the cylindrical coordinates. Remains one variable, which is the theta variable. I'll postpone this because it is a problem at the end of the chapter. We'll do it when we think of the problems. But try to think about it from now. What about if we have symmetry with respect to this and that, and we want to find the Laplacian as setting this is equal to 0 in the case of Laplace's equation, how to solve it, and what would the shape of the spherical symmetry be in that particular case. Okay, so by this I end paragraph 3, 11.4. That was 3.11.3 for the cylindrical coordinates and 3.11.4 for the spherical ones. We are still left with one subject in this chapter, which is the method of images. We'll start doing it next time. And until then, I say goodbye for you all.